In today's lesson, we're going to start with graphing quadratic equations in standard form. And so I do want to review a few things with you. You are writing nothing down right now. You are only paying attention to what is up here. If I provide you the following function, f of x equals x squared plus 6x minus 5, and I ask you to graph this, and we're not using any technology. The very first thing you're going to do is you want to figure out what is the vertex of the parabola. Remember, parabolas make this U shape, and for quadratic functions, the U shape will either open up or it will open down. And so we want to know what is the lowest point if it opens upwards, and if it opens downwards, which I will make right now, if it opens downward, we want to know what is the highest point. It's called the vertex. The vertex contains both an x value and a y value. So how do we go about finding that when we're not using any technology? This is the equation, x equals negative b over 2a. And you may be thinking, like, what is a and what is b? I see no a's and b's. A is always the value in front of the x squared. So a in this case is 1. B is always the value in front of the x, so b is positive 6. We include the sign. And c is the constant. It's the value at the very end that has no x stuck with it, so c is negative 5. So what I'm going to do at this point is I'm going to substitute in those values for b and a. X equals, and I'm going to put in parentheses where I'm going to drop in the b and a. So b is positive 6 and a is positive 1. And then I'm just going to do the math. This becomes x equals negative 6 over positive 2, so x equals negative 3. Okay, well, what does that tell me? If I go over to negative 3, 1, 2, 3, if I go over to negative 3, and let me make a new graph so it doesn't confuse you about how I just explained what a vertex looks like. If I go over to negative 3, 1, 2, 3, I'm going to make a dotted line going vertical, and always vertical for quadratic functions. What this dotted line does is it's going to cut the parabola in half. The parabola is symmetrical. The left side will look exactly like the right side, and it will be cut in half by this line called the line of symmetry, or the axis of symmetry. This is the equation for it. Now, in order to find the vertex, remember it has an x and a y value. I already know the x value is negative 3, but I need to now figure out what is the y value. So I come back to the original function. We know y represents f of x, so y equals, and wherever I see an x, I'm going to leave an empty space. And I'm going to fill in that empty space with what I determine x to be for this problem. X is negative 3. So in this position, I have negative 3 and negative 3. There's no calculators being used here. Make sure you're paying attention. Negative 3 squared means negative 3 times negative 3. 6 times negative 3 is negative 18. And now I'm just going to do the algebra. So 9 minus 18 is negative 9, and negative 9 and negative 5 gives you a negative 14. So this means I'm going to go over to negative 3, and I'm going to go all the way down to negative 14. I'm going to pretend it's right here, negative 3 and negative 14. Now, how do we do what we learned last week? So remember last week we talked about how we could use parent functions to graph absolute values, square roots, quadratics, cubic functions. We learned all about how we could take a function that's translated or moved left, right, up, or down, or it's been stretched or compressed, and we can use a parent function as a guide to graph it. We're going to do the same thing. So I'm working right now with quadratic equations. So on the front side of your paper, please look where it says class notes. One side says independent practice, one side says class notes. Please write down what I'm writing down right now in blue. This is the parent function for quadratic equations. When I have an input value of negative 2, I know negative 2 times negative 2 is 4. Negative 1 times negative 1 is 1. You are writing this down, 0, 0, 1, 1, and 2, 4. Those are going to guide me. Those are going to guide me in graphing. Now, you're writing down what I have in blue, right over here what I have in blue, and then you're going to put your pencil or pen down. And I'm going to demonstrate how we can use this to now graph this function. As a reminder, going back to what we talked about last week, we're going to look at the a value. When the a value is a 1, well, taking 1 times the y values doesn't change anything. 4 times 1 is still 4. 1 times 1 is still 1. 0. Doesn't change anything. This is my bullseye. My bullseye is always 0, 0. So how am I going to graph this? Well, this is 0, 0. I'm going to go 1 to the right and 1 up. You were just watching 1 to the right and 1 up. Then I'm going to go 2 to the right and 4 up. I'm going to go 2 to the right and 4 up. 1, 2, 3, 4. 1 to the left of the bullseye and 1 up. And 2 to the left and 4 up. And now I have this basic quadratic equation that models this. So if I gave you this random quadratic equation that's in standard form, the first thing I would ask you to do is to identify the A, the B, and the C. Now let's identify what the vertex is. The vertex and the axis of symmetry, also known as the line of symmetry, interchangeable terms. So we're going to use the same equation for both, and that is x equals negative b over 2a. So I'm going to start by replacing the b and the a with parentheses, and then I'm going to drop in what the b is. The b happens to be negative 4 for this equation, and the a is 2. 2 negatives on top in the numerator makes a positive 4, and 4 divided by 4 is 1. So I know the equation of the axis of symmetry is that x equals 1. If I make a very simple graph here, I'm going to go over to positive 1, and I'm always making this vertical line going straight down. It's going to be dotted through the x-axis at 1. It's always going to be through the x-axis. Jonathan, I need you to stand up and back. You can't stay away. Please stand up and back. Your eyes are shut. They're not going to be shut anymore? Oh. Okay. Here we go. Now for the vertex, we have 2 points in x and y. I'm going to replace the x with the 1. How do we figure out the y value of the vertex? I take whatever the x value is and I substitute it in for x. So y equals 2 times 1 squared minus 4 times 1 plus 5. 1 squared is 1. 2 times 1 is 2. 4 times 1 is 4. And now I'm just doing the math. 2 subtract 4 is negative 2, and negative 2 plus 5 is positive 3. So I'm going to find the point 1, 3. This is my bullseye. Now I'm going to write down what I already asked you guys to write down, and that is the parent function for quadratic equations, negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Partner B, please turn to your partner. What do I do to this list of inputs and outputs that belong to the parent function to help me in graphing this? I'm going to press whatever the a value is, I'm going to take it times the y. Now the only time you don't have to worry about that is if the a value is 1, because taking 1 times the y values doesn't change anything. 2 times 4 times 2 times 2 times 2. This is my bullseye. My bullseye is always 0, 0. From the bullseye, over to the 1 and up 2. Over 1, up 2. Over 2, up 8. Left 1 from the bullseye, up 2. Left 2, up 8. So I'm going to start with just identifying the vertex of the line of symmetry. My A value is 3, the B value is positive 6, and the C value is negative 2. Both of these will require the equation x equals negative b over 2a. I always suggest putting a parenthesis where you're going to drop on those values. It helps to prevent mistakes. So my b value is positive 6, my a value is 3. I end up with x equals negative 6 over 6, which reduces to x equals negative 1. By a raise of hands, who had x equals negative 1? Maybe you didn't get that far. So I'm going to come over here and write x equals negative 1. That is the equation for the axis of symmetry, also known as the line of symmetry. All right, then I'm coming over here, and I'm making this dotted line at x equals negative 1. Your vertex has 2 points. Sorry, it has 2 coordinates, an x and a y. Your x in this case is negative 1. So what I'm trying to show you is that your axis of symmetry value will always be the same as the x value for the vertex. Now, what's the y value for the vertex? Well, I'm going to come back here, and wherever I see an x, I'm going to leave it blank with the parenthesis in that position, and I'm going to drop in the value negative 1. Negative 1 squared, well, negative 1 times negative 1 is 1. And then I'm just going to go from left to right, and I'm going to evaluate this side. 3 times 1 is 3. 6 times negative 1 is negative 6. And from left to right, I end up with a negative 5. So this is negative 5. I'm going down to negative 5 and making a dot. This is my bullseye. This is my bullseye. I asked you previously to write down the inputs and the outputs of the parent function to quadratic equations. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. How is that going to help us? Whenever the leading coefficient, known as the A value, is anything other than positive 1, we're going to change the shape of this parabola, either making it skinnier or wider, opening up or opening down, and it's based on this value. So I'm going to take each of the y values times 3. 12, 3, 0, 3, and 12. And this may go off the graph, but let's see what we can do here. What does this mean? Well, 0, 0 is always the bullseye. I'm going to go 1 to the right and 3 up. 1 to the right and 3 up. 1, 2, 3. 2 to the right of the bullseye and 12 up. 2 to the right and 12 up. So 5, 7. 1 to the left and 3 up. And 2 to the left and 12 up. In standard form, that's all we're working with today. In standard form, the constant, the value that has no x's, is always the y-intercept. So let's write it as an ordered pair. 0, negative 2, we can see we have that on the graph. The domain here, this is going diagonally to the left and diagonally to the right. So as it's being pulled up, it's also going to the left. And as it's being pulled up on the right-hand side, it's also being pulled to the right. That's what's making this diagonal. So there's no limit how far this parabola moves to the left and to the right as it opens up. Now there is a limit on the range. We always go from the smallest to the largest. So this goes down as far as negative 5, and it's included on the graph, but there is no limit how high it goes. We worked with end behavior way back in Unit 1 in August. Now end behavior is looking like this. So we're going to look at the very far ends, the far left and the far right, and we're going to predict what is happening. So as I go to the far left, one of three things is happening. The graph is headed up, the graph is headed down, or it is staying constant at some value. So let's look. As I go way over here to the far left on the x's, what's happening? It is headed up. How do I represent that? Positive infinity. Now as I go to the very far right on the x's, when this eventually goes into that, it would also be headed up. Let's look right now at example number 2. I'm going to start off by identifying the A, the B, and the C. My A is 2, my B is negative 12, and the C is 7. Both vertex and the line of symmetry, also known as the axis of symmetry, will use the equation negative B over 2A. So I'm going to put a parenthesis where I'm going to drop in the A and the B. B is negative 12, A is 2. Two negatives make a positive, so I have positive 12 in the numerator, 4 in the denominator. How many of you had x equals 3? Hands up high. X equals positive 3. That's the equation for the axis of symmetry. So I'm going to go to positive 3 on the x-axis, and I'm going to cut straight through the x-axis, always making a vertical line. This line will cut my parabola in half. Now vertex has 2. A vertex has both an x and a y value. Remember, the value for the line of symmetry will match the x value for your quadratic functions. Now how do you find the y value? I'm going to come back up here and I'm going to write y equals, I know what the x is. The x value I want is 3. When you evaluate this, we're going to go through and we're going to use our PEMDAS. So 3 squared is 9. Then I'm multiplying to get 18, multiplying to get negative 36, and I'm going to go from left to right. 18 subtract 36 is negative 18, and negative 18 plus 7 is negative 11. So I want to find 3 and negative 11 and make a dot. I'm going to come over here, and just like we have up above, I'm going to write down the input and output values for the parent function of quadratic equations. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Okay, you ready? If you are the taller partner, turn to your current partner. If you're the taller one, what do I have to multiply by the y's? Go. What do you multiply by the y's? It's the A value. It is the A value. And this changes the shape, and sometimes it changes even whether it's opening up or down based on whether it's positive or negative. Times 2, times 2, times 2, times 2, and times 2. 0, 0 is always going to be our bullseye. So I'm going to go 1 to the right and 2 up. 1 to the right, 2 up. 2 to the right and 8 up. 1 to the left and 2 up, and 2 to the right and 8 up. My y-intercept can always be found in standard form as the last number when it's in standard form with no x. So 0, 7. The domain, there's no limit how far it goes to the left or to the right as it opens up. The range, it goes down as far as negative 11, and there's no limit how high it goes. So the first one, if I read from left to right, this means, hey, go to the very far left. And when our function eventually goes into that far left oval, which direction would it be going? It would be going up. So the y value would be going up. That's how we are identifying the end behavior on the far left. Now let's identify the end behavior on the far right. So as it goes into this oval, it is also headed up, positive infinity. What you're going to notice about quadratic functions is these will always be the same. They're both going to be positive, or they're both going to be negative. Let's look at number 3. I'm going to start by identifying the A, the B, and the C. Next, we're always going to use the equation x equals negative b over 2a. So I'm going to put in parentheses where the A and the B go. The B is on top, the A is on the bottom. 2 negatives make a positive, and 2 times 2 is 4. So I have x equals 2. This will always be the equation for the axis of symmetry. So I'm going to come over to positive 2, and I'm going to make my dotted line. Your vertex always has an x and a y coordinate. The value for the line of symmetry is always the same as the x value for the vertex for quadratic functions. Now, how do I find the y? I'm going to write down the equation, and wherever I see an x, I'm going to replace the value x with what I've found, which is 2. Okay, let's use PEMDAS. So first I'm doing exponents. 2 times 2 is 4. And now I move on to multiplying and dividing. 2 times 4 is 8. 8 times 2 is negative 16. And I have negative 8 minus 3. I end up with y equals negative 11. By a raise of hands, 2 ends up with negative 11 as well. So I need to graph that 2 and negative 11. And then I write down the same set of input and output values that we have been working with. Okay, whoever's shorter, turn to your partner. What do I multiply by the y's? What value do I multiply by the y's? 2 for this problem, whatever's in front of the x squared. So times 2 is 8, 2, 0, 2, and 8. And now I go back to this point. This point, known as my bullseye, is always 0, 0. I'm going to go 1 to the right and 2 up. 1 to the right and 2 up. 2 to the right and 8 up. 1, 2, 3, 4, 5, 6, 7, 8. 1 to the left and 2 up. 2 to the left and 8 up. What is the y-intercept? It's always going to be the value at the end with no x's, so 0, negative 3, and we can see that. The domain, there's no limit how far it goes to the left or how far it goes to the right. The range, it goes down as far as negative 11, and there's no limit how high it goes.